Here's a nice Excel spreadsheet done by William F. Coleman from Wellesley College that shows a Maxwell Boltzmann curve. And right now in this curve, we've got about 1 mole of oxygen gas. It's got a molecular weight of 32 grams per mole. Now, notice it says the area underneath the curve is 1. That stands for 1 mole. So we've got 6.02 times 10 to the 23 molecules of oxygen gas bouncing around in here. Each one of these takes up a little bit of area. The area underneath the curve is the number of molecules, which in this case is going to be fixed. We're going to keep 1 mole in this entire plot area. Now, the average here, the average is going to be like the peak of this curve. I mean, we've got some molecules that have a faster kinetic energy, and because this is their speed. This is their speed in meters per second. These guys are moving very quickly. They've got a pretty high kinetic energy, but these guys are moving slowly and have a low kinetic energy. And the average is going to be, because this is a skewed graph, which got, it's not symmetrical. It's going to be a little bit to the right of the graph, and it turns out to be 364 meters per second. So the average molecule here has got a speed of close to 400 meters per second. But of course, there are some that have got a higher speed and some have a lower. In fact, theoretically, you could end up having some molecules out here at 2,000 meters per second, but not many. I mean, their fraction is going to be minuscule. The total amount of kinetic energy, if you were to measure the energy of these bouncing molecules, would be about 2.5 kilojoules. This is at 200 kelvins. Now, we're going to keep the temperature the same. So these molecules are still going to end up having the same kinetic energy. But what we're going to do is we're going to switch their atomic mass from oxygen down to the next lower molar mass elemental gas, which is nitrogen. So I'm going to go from 32 grams per mole to a total of 28 grams per mole. Here we go, 30, 28. Now, take a quick look. I can go back up to oxygen. There we are. And now to nitrogen. Same kinetic energy. Still 2.5 kilojoules. Same number of molecules. But notice our curve is lowered a bit. And that's because the curve spread out. Some of our molecules ended up having a higher kinetic energy. And we still have some with a low, but not nearly as many. So the curve has dropped down a bit because we have to have the same number of molecules just spread over a wider speed range, because these lighter molecules have got to bounce around a little bit faster. I mean, they don't have as much mass, so they've got to bounce a bit faster on the average to still have 2.5 kilojoules worth of energy. Well, let's switch down to the next gas that we can have at 200 Kelvin that I was able to find, which is methane. Now, watch this curve. We're going to 16 grams per mole. Here we are. Oh, I went up. Let's go down to 16 from 28. Here we go, 26. And that curve gets, let me just get back up to right now 16 grams per mole. And you can see the curve peak is lower. But now we have a whole bunch of molecules traveling at 1,000 meters per second. Go back to oxygen, and no way. Here we are at 32 grams per mole. The amount of 1,000 meter per second molecules are very few, but with methane, our lower molar mass, with a total of 16 grams per mole, we've got a considerable amount of these, but these are lighter. So even though they're moving at 1,000 meters per second, their kinetic energy isn't increased any because they are lighter. They don't weigh as much when they bounce against the walls. Now let's keep on going. Let's go down to the next lowest molar mass gas that we have at this temperature, which is all the way down to helium. Now here we go, and watch this curve. Area underneath the curve is the same number of molecules, 1 mole. So here we go, lower molar mass, 8. There's no gas that is at 200 Kelvin is 8 grams per mole. Let's get down to, here's helium. Helium, 4 grams per mole. And now the average is pretty close to 1,000 meters per second. Before, there was nobody at 1,000 meters per second, but now there's so many of them because these guys have to move faster to maintain the same kinetic energy. Now, this graph keeps on going. It's just that we don't end up, I limited my graph to 2,000 meters per second. And let's go all the way to hydrogen here. Down to hydrogen. Here we go. 2. And now it looks like our average is closer to 1500. If you take the regular average, not the root mean square average, which is pretty exotic, it's close to 1500 meters per second. When before, with oxygen, 16 times the molar mass, we end up having an average speed of only, here we go, let's move that up to 32 grams per mole, 360 with almost nobody at 1,000 meters. So this is our Maxwell Boltzmann curve. Have to move faster to have the same kinetic energy, but the peak of this curve lowers because we've got to distribute that same number of molecules, which is the area underneath the curve, over a wider range. That's the Maxwell Boltzmann curve and molar mass.